Yes, sir.
All right. Okay, so first of all, welcome back. And secondly, let me see where we were. Let me share the screen. Just give me a second. Okay, so can you see the screen? Is it visible? Yeah, so can you see the screen? Is it visible?
Yes, sir.
Okay, great, great, wonderful. All right, so give me a second. Okay, all right. So we were doing this thing. We finished the topic of ideal gases with the topic of adiabatic expansion and compression. The goal today is we'll be doing some of the problems for from this chapter, and then we'll start the next chapter of waves and oscillations, right? So let me okay. All right, so is there any questions from anyone from the last lecture that we did?
No, sir.
Anything regarding can you remind me if I shared the notes? I think I did, right? For ideal gases up until we covered, I think I shared the notes as well with you guys in the group.
Yeah. Yes. Yes.
As far as I remember. Okay. All right. Okay. Good. So hopefully you went through those, and if you did not, it's all right. You can go through them, and if you have any questions, you can always ask me. I did not have the time to check any of the quizzes. I know we have 3 quizzes, I think, and you don't know the marks yet, but I'll very soon give you all your quizzes. I was also thinking if I prepare a marking scheme for those quizzes and share that with you, and if you have any problems, so you can just WhatsApp me those problems that in this question I could not this can you do this question in the class or that question in the class. Maybe that's one way we could check these quizzes speedily. Otherwise I'll have to go through all your quizzes, and I'm also teaching O levels and AS level and others as well, so it's kind of hectic for me as well sometimes to check all the quizzes one by one. So if you think that this would be okay if I share the marking scheme with you guys, so you can compare your answers, and if you have any problem in a specific question, how do I, if you don't understand them even from the marking scheme, then I can do those questions in the class as well, and you can tell me that this particular question is we are having problem in that. Does this sound okay, or do you want me to individually check all the quizzes? Any it's up to you guys. Anyone? So these are the 2 options, right? One is I'll check one by one. The other option is I'll share marking scheme, and you can personally message me that I have a problem in this question. Could you please solve this question in the class? And then we'll only solve those questions in the class. Or we can also, in fact, arrange a class where we solve all of the quiz. But the only thing over here is that I would not have to check the quizzes one by one for every student, as I have to do that for AS, A2, O level, and NET, or those kind of things as well. So do you think the marking scheme option is better? If you have any questions again, so we'll do them again in the class as well. Okay, it's all right. So I think we have spent a lot of time on this discussion. You can let me know in the, so this is one suggestion. You can also let me know in the group after the class, which option do you guys prefer? All right. Okay. So the goal for today is then to solve some of the problems. These problems will be more or less based on internal energy. All right. Okay. So first of all, just a very simple problem. And it's a question, really, a conceptual question, which I would like you all to help me figure out the answer to this, right? Suppose that I have a hot object, right? Suppose this is a container. And in this container, suppose we have hot water, right? And now let's suppose that there is another container and we have cold water again, but it's cold this time. And let's connect these two by some mechanism which allows the flow of heat, right? So heat, this is telling you that this is how heat flows. Ignore the arrow, right? Ignore the arrow. But it's your job to tell me the direction of the heat flow, and also tell me why would it be that direction. And one of the things is, you will be thinking in terms of internal energy as well. So for example, this is the situation. You have one hot water reservoir and then you have a cold water reservoir, and you have allowed the heat to transfer or flow between the two. Now the question is, in which direction do you think would the heat flow? First of all, you all understand the concept of heat? Is it clear for everyone? The concept of heat flow. We talked about it in the previous lectures, and the main thing over there was that there is only heat that flows. There is no such thing as cold which flows. Cold is just the absence of heat energy, really, right? So if there is an absence of heat energy, then you call that thing, you just say that it's cold. But there is no such thing as cold flowing from one body to another. It's only the heat that flows. So the less the heat, the colder the object gets. That's just it, right? So that's heat. Anyways, and heat transfers by different methods. So if you heat up something, it transfers by the vibrations of those molecules. They start vibrating more and more. And that's how heat energy transfers into other forms of energy as well. Anyways, what do you think would happen in this problem? Where would the heat be flowing? In which direction would the heat flow?
From the hot towards the cold.
From the hot body towards the cold body. Okay, so I'll tell you that that is the correct answer, right? So that's where the heat would flow. But now, so what is your justification for this? Why would you say that it would flow from a hot water to cold water?
It's like the concept of diffusion, I'd say. Temperature flows in a fluid-like way from the hotter one to the cold.
All right. Okay, but I mean, why though? Why? Why does the universe work this way? You're absolutely right. But why? Why not? Why did the universe or nature specifically chose this thing instead of the other one? And the answer, by the way, also lies in this thing, that there is no such thing as cold. There is as in there is no cold flowing. There's only heat that flows. So why would you? I mean, just a guess. Take a guess. Think about it, and just throw your guesses. Why would it be that the nature specifically chose this thing instead of the other one? Any guesses from anyone in the class? No guesses. Everyone is quiet today, I guess. Okay, so think about this. We have talked about the concept of equilibrium, right? Equal temperature. So equilibrium is the most stable state that a system can occupy, right? And the universe always flows or goes towards a minimum, right? Anything, and the universe wants to minimize everything, whether it's energy, whether it's, you know, whatever it is. In higher level physics, we talk about a term called action, and we minimize that to understand what path a system would take. And so the universe really wants to minimize everything. Now in this case, because suppose that I'm going to give you an example like this. Suppose this is a body and it's at, suppose it's at 100 degrees Celsius. And then there's another body which is, suppose it's at, well, suppose it's at, you know, maybe 200 degrees Celsius. Now let's connect these two bodies. And so why are we connecting? So that the heat can flow from one body to other. Now it happens that heat has to flow so that it can make the system stable, or it could make the system reach an equilibrium state. At this point, when this is 200 degrees and this is 100 degrees, the heat is going to flow. But you could say the heat, maybe it could have flown from this way to this way, or it could flow from this way to this way. The universe chooses this direction because it wants to make the system reach an equilibrium state so that everything is balanced. And to do that, the heat has to flow from 200 degrees to this box 100. And it will only flow, the amount that would flow would be only barely enough to make these two temperatures the same or reach an equilibrium. So what that would mean is only 50 degrees from this thing would go over here. So this would become 150, and this would become 150 as well, right? So both of these bodies, they reach a same temperature. And as soon as that happens, now there will be no heat flow. Heat flow would stop. So the universe wants to make the system stable. And the system is stable in its equilibrium state, right? Even though we know that the internal energy of this system would be higher compared to the 100 degrees Celsius. So the hot water system would have a higher internal energy compared to a cold water system. And the flow of heat is really, it does not really depend on internal energy of the system, right? So it doesn't matter whose internal energy is more. It only matters that the universe wants to make their system reach its equilibrium state. So is that clear for everyone? Does that make sense to all?
Yes, sir.
Okay, good. So, all right. So if that's clear, then that's good. This was really to make you understand the concept of heat, really. And if it's clear, then I would suppose or assume that the idea of heat is clear for everyone now. So you must always remember that there is only heat that flows. There is no such thing as cold flowing. So the only absence of heat from something means that it's getting cold. All right. Okay, let's consider another problem, another question. And this would have to do more with the first law of thermodynamics, right? And the question goes something like this, that suppose that you have a person and he wants to stir water, stir like mix water using some pedal or anything, right? Or a spoon or whatever. Uh, Suppose that this person, suppose, I don't know, maybe this is a container, there's water in this container, and there is a pedal, and the pedal will rotate about this axis and it will start stirring the water, right? Suppose the amount of water in mass is 2 kilograms. And suppose when I rotate this paddle to stir the water inside, I do 30 kilojoules of work. So the work that I'm doing in rotating this paddle is 30 joules or whatever, right? And the mass of the water that I'm trying to stir is 2 kilograms. Now, suppose while I'm stirring, suppose that, well, it's in calories, but well, we'll see how we convert calories to joules as well, right? So while I'm stirring, suppose that 5 calories worth of heat is released from the water, right? Because we know that when I stir, when I'm doing some work on this water by stirring this pedal, there will be some heat that would be released, because when I'm stirring the water, the molecules in water start vibrating more and more and more, and the vibrational motion of molecules correspond to the kinetic energy of these molecules. And we know that kinetic energy is directly related with temperature by this equation. Kinetic energy is 3/2 kT, right? So now the heat would be released, and that heat released is worth of, let me write it over here. So some heat is released outside, which is 5 calories, right? And this heat is transferred through all the surroundings, right? And of course, obviously, this container, surface of the container, which is also made up of atoms, so some of the heat would go in that as well. And it is done by, we all know, conduction, right? Conduction and radiation. So we want to figure out how would this process change the internal energy of the system, right? How would this entire process change the internal energy of this system? So what would be the change in internal energy of this system? So I repeat the question. I'm someone who's doing some work on this water by stirring it, and the water is 2 kilograms of worth of mass, and I'm doing 30 kilojoules of work by rotating this pedal to stir the water. And while the water is stirring, 5 calories worth of heat is being released from this entire system into the surroundings. I want to see, by doing all of this, by how much have I changed the internal energy of the system, right? So is the question clear, by the way? First of all, is the question clear to everyone? Is it clear?
Yes.
So you understand what's happening, right? Okay, good.
Yeah.
All right. So first of all, we need to be clear with our conventions. We defined, if you remember, in this problem, heat is being released. So what should be the signature with heat? Remember, we defined that Q is negative when we are transferring energy from the system to the surroundings. So the heat, and even in our question, this is exactly what's happening. From the system, the heat is being transferred to the surroundings. So it would carry a negative signature, right? So I'll say that the heat transferred is -5 calories. And to convert from calories to joules, it's just a matter of conversion. You just multiply. One worth of calorie is worth, I think, 4184 joules. So in place of this thing, I wrote this thing, right? And this just means are being multiplied. And so this would give you, I don't know, minus 20, 920 joules, right? So it would give you this. So this is the heat that is being released when I'm stirring the water to the surroundings, right? And the work that I'm doing to release this heat, right? Obviously, because if I was not stirring the pedal, I would not be doing any work. And if I would not be doing that work, I would not be causing any heat to release really because of the stirring. But because I am stirring, the heat is being released. So the source of this heat being released is this work that I'm doing, which is 30 kilojoules. That is, we all know, 30,000 joules, right? 30 kilojoules. All right. Now we know that the first law of thermodynamics is what relates these three variables, delta U, Q, and W. The internal energy of the system, the heat that is released or absorbed, and the work done by or on the system. And we know that the equation for that was, if you remember from the previous lectures, its change in the internal energy is simply equal to the heat minus the work. Now it's just a matter of putting in your variables. The only thing that you have to understand is what signatures would each of these variables carry with them, right? And that is why I have shared these notes with you, and I've shared this is the sign convention that we all follow. So you can just go through these again, but the change in internal energy is positive if obviously the internal energy of the system is increasing. It's negative when the internal energy of the system is decreasing. The heat is positive if I'm transferring heat to the system. If I'm giving my system some heat, then, or for example, suppose that when you put a water in a pot on the stove and you light up the stove, you're giving your water some heat, and at that point, the heat is positive. But in our example, where we're stirring the water, we're doing some work on this water and the heat is being released from the system. So in that case, it's negative. So transferring energy from the system to the surroundings. And again, work done is positive if it is done on the system, if I'm doing some work on the system, right? So in this case, I'm stirring the pedal. So I'm doing work on the system. So it should be positive. And if it's negative, then work is being done by the system. So now this convention, it depends on you. What do you define it to be? Whether you can say that I'm taking it negative, then you should be changing all your conventions. If you're taking it positive, by saying that positive means that work is done by the system, then you should change all your conventions accordingly. So it's better not to change anything, just stick with one so you don't get confused, right? So these were our conventions. Now let's just solve this problem. It's just a matter of putting in the values, right? Now you just put in the values for Q and put in the values of W in this equation, and it would give you some value for delta U, right? So that's your question. And you would see that this would give you the change in internal energy as, I think it gives you something 980 joules. And this means that the heat lost is less than the work being done on the system, right? We can see that clearly. We can see that from this expression. And that's why the change in internal energy turned out to be a positive number. So was this clear for everyone? Do you understand how we would compute the change in internal energy of the system, and with that, the sign conventions, and why did I say, what I said? Is that all clear, or is there any confusion? If there is any confusion, feel free to stop me and ask me. Right?
I do, sir. Why did we
Yeah.
take work done as negative? Didn't Q be taken as negative?
Q is taken to be negative, right? Minus 2920, and then this should be positive, because we're saying that work uh, is done on the system, right? So
Yeah.
maybe I think this calculation,
In
maybe
the
yeah. So,
equation, actually.
oh no, the equation is like this. Now, when I put the values in this equation, so for example, I'll tell you what we'll do. So Q, I'll put Q as minus 20920 joules, and minus work done, I'll take 30,000 joules. Is that clear?
Okay, yes.
All right. So now let's do another problem. And in the next class, we'll be starting the next topic, right? Waves and oscillations. So let's do another problem. And okay, so there is another problem that has to do with this first law of thermodynamics, and it's a very simple one. So let's just do this one, and then we'll move on to a problem that is regarding the PV diagram, right? Pressure volume diagram. Okay, so it's a very simple one. This one, consider that you go on a run or a jog, really, right? Now, suppose that there's a track, and you're just, just jogging on the track, because jogging every day is really good for your health. So you decide to jog. Now, when you do that, suppose that the work that you are doing while you jog, numerically, suppose it may be equal to 500 kilojoules, right? And suppose that when you jog, you know that you sweat, right? You sweat because you're giving off heat, right? Your body is radiating heat. That's why you're sweating as well, right? Well, the consequence of that is sweating. The process of sweating has its own biology. We'll not get into that, but yeah. So you're giving off heat, right? And that heat, suppose that you're giving off from your body to the surroundings, is worth of maybe 230 kilojoules. Okay, suppose this is the case. How would the internal energy of your body change? That's the question. Now, again, the equation that we would be using is very simple, but the signatures is what we have to be sure about, right? So we know that it's just the change in internal energy is Q minus W. So, okay, so when you're jogging, you do work of worth about 500 kilojoules, right? So the work is being done by you. The environment or any other thing is not doing any work on you, unless, suppose, I mean, you could argue that I didn't want to jog, but this other person forced me to do it, so he was making you work. But that's not the language that we're using. You're jogging, you're doing your body is doing the work, so you're doing the work, right? So you'll say that this work then is a positive quantity, so it's positive 500 kilojoules. What about the heat? Heat is being released from your system, from your body to the surroundings, right? When you're jogging, you're radiating heat. That's why your body gets hot, and you transfer that heat to the surroundings. So the body is releasing the heat from itself, and that's why it should have a negative sign. So negative 230 kilojoules. Now it's just a matter of putting these into this equation and this equation and solving for the change in internal energy. Does that make sense? Is that clear? It was an interesting problem as well, so I thought, why not?
Yes, it's clear.
Okay, amazing. Okay, let me just check how much time do we have left. We have about 5 minutes remaining. Okay, so we can do this other problem, and this would probably be the final problem, and then in the next class we'll start the next chapter. Okay, so we have space over here, so let's utilize that. Suppose now that you have a container of gas. Let me try to draw it. It's a cylindrical container, and there's some gas in this container, right? And this is the piston. Now, there's some gas filled over here. So this is just that gas. And it has a volume V and some pressure. Some pressure that there is in this container because of this gas, which is P, and some temperature at some temperature T. So there is these three variables are here. Suppose that I put sand particles on top of this thing. So I'll use some other color. Let's use this thing. So I'm putting sand particles on this. And let's say that I'm so gentle that I put one sand particle at a time. So one by one, I'm putting all these sand particles and they jumble up on this piston. Eventually, obviously, what will happen? The piston would eventually start going down, right? Everybody agrees with that? The piston would start moving inwards slowly. All right. Okay, so this type of process is known as a quasi-static process, by the way. This type of process is called a quasi-static process. What that means essentially is that I'm not changing the pressure or any of these variables instantly. Because if I change them instantly, then the process would not be, it would not be an equilibrium process as well. What I want to do is I want to change these variables so slowly that, if I put one by one sand particles, I'm doing the process so slow that it is allowed to be a quasi-static process. So this is the case. Now, what would happen? I'm going to tell you that okay, what can we calculate in this problem? Let me think. I did not prepare this question fully. Let me think. Okay, suppose the idea was to make you understand what would be a quasi-static process, really, right? And now suppose that I don't have this, I don't have these sand particles. I don't put any sand or anything on this system. Suppose it's just a gas. So I think I'll say that it's another problem. And suppose that again the gas is in this same thing, but there is no sand particles. Then the gas, suppose it expands after some time from some volume V1, which is 1 meter cubes, to some volume V2, which is 2 meters cube. And suppose this happens when the pressure is constant. The atmospheric pressure, we all know that there is some pressure from the atmosphere because there are particles in the atmosphere, and that pressure is constant. It does not change. We are required now to compute the work that is done by the gas, right? So atmospheric pressure is 1 atm, right? We all know that it's 1 atmospheric pressure, which is equal to in pascals 101 kilopascals. right? So these are the variables that are given to you. And suppose the final volume, which is V2, well, we have written these volumes, and we know now how can I compute the work done by the gas if this is the system. Can anyone tell me? We have looked at this kind of problem before as well. Can anyone tell me? We have less than 1 minute remaining, so I'd like someone to tell me very quickly how would we compute the work done by the gas. We'd use this expression, right? Work done is the integral P dV, or simply you can say P change in the P times change in volume. That's the expression for work done. We have seen this expression before as well. And this would be pressure is constant, right? We are given that it's just 1 atmospheric pressure, then the change in volume is V2 minus V1. Put in the variables, and then you'll calculate the work done. So is that clear?
Yes.
Yes.